podcast is brought to you by LMU Munich.
Good morning. Let's get going with our second lecture. There are copies of the first lecture outside. Perhaps you picked one copy for yourself. Those are the notes that I've been writing. And they will be helpful at least for the first half of today's lecture, because I'm going to just pretty much complete the things that I was doing last time. And the notes will help me write a little less on the blackboard and try to just give you a picture of what's going on rather than having to do lots of algebra. Then we'll turn to this second subject of what was supposed to be the subject of the second lecture, and discuss Courant brackets and the doubled field theory itself. So those lecture notes will be available this afternoon, or actually just right after the lecture, so please get them as well. So let me just remind you of a couple of things we had from last time. So we learned about an object called a generalized metric that depended on this field E that was describing the background, which was Eij equal Gij plus Bij. And this object was a rather intricate matrix of size 2D times 2D, symmetric matrix. That's why it was called a metric. And it had this form, 2D times 2D. There was also a metric eta. And all those matrices are 2D times 2D, where Gij, G, and B are just D times D. So those were some of our ingredients. Then from the first quantization of the string, we also got some differential operators that were supposed to be important for us. So these differential operators came from the zero modes of the string, and they formed what we call these derivatives in equation 10 of the notes. So we had two derivatives. A derivative di that includes derivatives with respect to the usual coordinates, the dual coordinates, and a bar derivative, which include a slightly different combination, different sign, different order of indices here, and that. So the string theory told us those were important. Then we lower or raise indices with the metric G. So you could define the D with upper index, or you could define D squared, which was Di, and D bar squared, which was D bar I. And in particular, D squared minus D bar squared was proportional to this kind of Laplacian, in which we had a derivative with respect to a normal coordinate times a derivative with respect to the dual coordinate. And we learned that in fact this combination was related to L0 minus L0 bar. In fact, the operator L0 minus L0 bar, when you look at massless states, reduced to essentially this. And since that operator must kill all states of a closed string theory, we expected that this differential operator will kill all fields of the double field theory. So this is something that comes from the string theory. Finally, we focused on the ODD transformations. We had this ODD matrices H that satisfy H transpose eta H equal to eta. We wrote the matrix H as A, B, C, D. And A, B, C, and D were all D times D matrices. So H again is a 2D times 2D matrix. This has to do with the group ODD. These matrices form the group ODD. And we looked at the invariance of the Hamiltonian. The string Hamiltonian was supposed to be left invariant by these things, and that required first that this be true, and then it required that H of E prime be equal to little h, H of E, H transpose. So lots of H's, but we'll keep them straight. So we need this. And we said that E prime had to be different from E, and H would control the relation between them. And we wrote E prime equal H of E, or A, B, C, D, E. And we said this meant AE plus B times CE plus D to the minus 1 in terms of matrices. And let's see. There was an exercise, there was exercise 5. I'm looking at page 10 of the notes. And we concluded by looking into proving this equation that this would be true if E prime is related to E in this way. So that was our goal. For that, we started with the construction of this object that we would call H sub E that creates the background E starting from the identity. And if we wrote E as G plus B, where G was A times A transpose, then we showed that H of E, which is given by A, B, A transpose minus 1, 0, A transpose minus 1, was the answer in that HE acting on the identity background would create E. So this is as far as we got last time. So that was a quick review. And now we're going to move forward. So if there's any question at this moment that you have, please go ahead.
So you gave an exercise that E prime transpose is related to E prime by E transpose by some matrix.
Right.
So suppose I take E to be identity. So how is it then these two things?
Well, the exercise is a totally unrelated exercise. This exercise 5 asks you to prove that E prime T, so exercise 5, asks you to prove that E prime transpose is A minus B minus C D of E transpose. And this is, not related to this calculation. It's just a way of relating the transpose matrix to the transpose E to the after the transformation. So it should follow from this. Now it's a little challenging, nothing very difficult, but you remember we wrote several formulas for the matrices, the identities satisfied by these matrices, and you have to use them and have to look at this the right way. This is the kind of problem that you either solve in 5 minutes, if you sort of see your way through the algebra in an easy way, or you can go in circles for quite a lot of time and not quite show it. But they're nice group theory exercises. Now, okay, so let me say one more thing here. When we determined HE, we wrote one HE and we said it was not unique. And indeed, HE is not unique because there exist G's in ODD such that G acting on the identity still gives you the identity. And that causes an ambiguity, and the ambiguity is obvious. You could replace HE by HE times matrix multiplication times G. So if you act now with this one on the identity, well, G does nothing to the identity, and HE produces for you E. So this is an ambiguity. As long as there are things, ODD matrices, that act on the identity and leave the identity over there, you are going to have ambiguities. So exercise 6 on the notes goes into discussing what G is, and the set of G's, as exercise 6 says here, is a set that form a subgroup of ODD. So not all elements of ODD, of course, do this, but a subgroup does. So G actually belongs to an OD times OD subgroup of ODD. And in fact, G transpose G is equal to G transpose equal 1. And those are things you will have to show. And there's a little bit of a hint on how to do that at the bottom of page 10 and page 11. So these are exercises on ODD transformations, on duality transformations, and they're pretty nice and simple. But again, take a little ingenuity to get them right. So okay, so once we have that, we were really aiming to show that H transforms this capital H or calligraphic H of the E, transforms the right way, and this becomes a rather straightforward thing to do. So it begins with a calculation. If you have HE, you can multiply it by HE transpose, and that, by definition, is a symmetric matrix. So this could be a nice symmetric matrix because it's an important matrix and it's symmetric. So we can just try to calculate it. We have A, B, A transpose minus 1, A transpose minus 1, A transpose 0 minus A minus 1, B, A minus 1. So I took the transpose of this matrix and wrote it here. And now we can begin to multiply. Well, here you have A transpose. You recognize that. That's G. And then this B, A transpose minus 1 times minus A minus 1B. But that minus, you see, there's a B. There's the A transpose A minus 1. and that's just G minus 1, and there's B here. You go for the next one, and you see actually you're getting B. A transpose minus 1, A minus 1 is G minus 1. Well, you'll believe me if I just say the end result is, in fact, H of E. So that's fabulous. So good, we know what H of E is. So now, if we want to know how H of E transforms, we just need to know how this little thing transforms under a background change. So that is actually straightforward. Suppose E prime is some transformation that gives you E. So look at this. E prime is what you would call H of E prime acting on the identity. On the other hand, this is H of HE acting on the identity. But these things are groups. So H of HE acting on the identity is nothing else but H, matrix multiplication, HE, all of that acting on the identity. Therefore, we have that HE prime is equal to HHE acting on the identity. So you would say, oh, then HE prime must be equal to H times HE. And when you say that, you say, not quite. Well, there's a little ambiguity because there are things that act on the identity and leave it invariant. So yeah, it's this, but it could be times some G, where G again belongs to this OD times OD subgroup. So where G is such that G transpose G is equal to G transpose equals to 1. So this is what we've learned. So now we can finally do this. H of E prime, because of this property, is equal to HE prime transpose. But HE prime is equal to HE G, and HE prime transpose is G transpose HE transpose H. The GG transpose disappear, and you get HE transpose H. I'm missing a transpose here. And therefore, this is H, generalized metric of E, H transpose, and that's what we wanted to show. So that is the way one can prove that the generalized metric transforms. And the generalized metric is therefore a rather beautiful ODD object, transforms by similarity on the two sides. It's an important property, and this metric has been so famous that mathematicians use it, and physicists always thought, well, there should be a way to think of this metric as something even better than the G and B. And one of the things that we're going to be showing is how to write the Einstein action plus the antisymmetric action and all that, not in terms of G and B, but in terms of that capital H directly. Okay, so we need a little more of technical things to prepare the ground. So I'll go through them with the help of the notes, and basically want to give you a feeling of what's happening. So we said that we have E and E prime, and they're related in intricate way, this linear fractional matrix transformation. So it's not all that easy to see how G and B transform. So you need a little bit of ingenuity to relate G prime to G, and there's one formula that does it. I'll write it here. G prime and G are related this way. It's sort of interesting. It doesn't involve the A and B matrices of H. When we're doing our duality transformation, of course, H has A, B, C, and D, but only C and D and E itself enter here. So this is the relation between G prime and G, and you would say, well, it's even not all that obvious because there's a matrix here and G is in here. So, well, but in a sense, G prime, you could put this matrix to the other side, this matrix to the other side, and G prime is determined. But this is also interesting because G prime and G are related by a matrix acting from one side, a matrix on the other side. That's a tensorial transformation, but a slightly more complicated tensorial transformation than the one of the generalized metric. H just enters here and it's very easy. Here, G and G prime are related by matrices on the two sides, and they're not constant matrices. They depend themselves on E. So it's a little peculiar. Now, this will lead to the idea that there are two kinds of indices in this theory. Indices that transform with this matrix and this matrix as well. This is basically the same matrix, just transposed on one side and the other. So this G object has some kind of indices that transform with this matrix. And we'll see more about this. But actually, the metric G is fabulous. It's an object that is very peculiar. It transforms with this thing, but happily, there's another set of matrices that also transforms G. So in fact, there's another property in which G prime is actually equal to D minus CE transpose, and here D minus CE transpose, and that's also equal to G. Both hold. And that will have some meaning. So actually, to sharpen the notation, we'll introduce matrices M equal D minus CE transpose, and M bar equal D plus CE transpose, so that these relations can be written as G equal M bar G prime M bar transpose. That's this equation. And I put the left-hand side G here, and there's all these things. And then G is also equal to M G prime M transpose. And the matrices M and M prime will be important in our development. I was talking about indices. If you write this out, you could say that G, say ij with bar indices are equal to M I bar P bar M J bar Q bar G prime P bar Q bar. That would be a translation of this formula with bars here. And the translation of the other formula would be that G, you could also think of it as having normal indices, not barred indices. It's the same G. It's not different. So I could delete the indices maybe for clarity. But what I want to say is that in some sense you can think of G as an object that has either kind of indices. So, for example, if I write this as MIP MJQ GPQ, I could write both equations without putting bars on the indices, and you would say, sure, they're fine. But these are indices that transform with m bars. These are indices that transform with m. And G is a very peculiar object. It's a tensor that can either use one kind of transformation or the other. It's some sort of interesting property of these tensors. So let's push these blackboards up. So, one more piece of information. You're starting to see, I hope, there's two kinds of objects. Objects that transform with H, like the generalized metric. The H of ODD just acts on the left and on the right. And then there are objects that transform with these matrices M. So those are the two main kind of objects in this theory. So you could wonder, what's the usual relation between those objects that you suddenly go from one object that transforms with the H, little h, and objects which transform with the M's. So here is the little lemma or theorem that tells you how to go from one object to the other. So we say that some object, for example, that has components like this, is a fundamental of ODD if, say, theta prime, like that, transforms just with H on theta, like that. So I suppress the indices, and I say the new one is equal to H on this one, or is equal to A, B, C, D, theta tilde theta. Okay, so this is what we call an object that transforms in the fundamental representation of ODD. Now you can define two different objects. An object y sub I, which would be minus theta tilde I plus eij theta j, and yi bar, which would be theta I tilde plus eji theta j. So define two more objects using the thetas and the e's. Once you have the thetas and the e's, these two objects are not going to transform anymore with A, B, C, and D because they have the E in here. They're going to transform differently. The nice thing is that these two objects transform with the M's. So this is the general statement of how you go from an object that transforms with H's to an object with transform with M. So then yi is, for example, mij yj prime, and yi bar is m bar I yj bar. I put a bar here. In the notes, there's a bar missing in equation 32 in the second one. Excuse me? And the prime is also missing, yes. Two typos. Okay, so again, let's not try to do very concrete calculations right now, but just appreciate the kind of objects that exist in the theory. Objects that transform with H, objects that transform with M's and M bars, and they're related in this way. Well, this has a very nice application. Our coordinates naturally are grouped into the dual coordinates and the normal coordinates, and as such transform in the fundamental of ODD. A duality transformation precisely also changes x's and x tilde, mixes them. That's what a duality is supposed to do. So h, this little h of ODD acts on this, and this is a fundamental, it's an object like this. So actually the partial derivatives, it's also column vector, but now with a lower index. Partial derivatives always are naturally with a lower index. And in order to produce a Kronecker delta with these xm's, they have to go like di tilde, di like this. So the first goes with the first, and the second goes with the second. Now, in this theory, we are lucky that we have this eta that we said this eta matrix could be thought as this, or like that. Eta as a matrix is 0, 1, 1, 0. And it can be thought as a matrix that lowers and raises indices. So in this theory, we can write dm up as eta mn dn. And this switches the position of these two. So you get a di down, the tilde I up. So, okay, so we're trying to do an application of these ideas. We're almost there. I can't resist doing one more thing before doing this, is to compute what is dm. This should be an ODD scalar. The indices are contracted this way. And we can calculate it. Well, you put this dm and that, and when you multiply them, you get twice d tilde. So our constraint is also, in ODD covariant language, this thing equal to 0 is the constraint. Okay, so where is the application? Well, the application is now coming. We have this thing in the fundamental. These derivatives transform with little h. Well, what transforms with m? What kind of derivatives? Well, it says here that you should take the lower component with a lower index here. You should form something like minus di plus eij d tilde j. That should be a nice object. And this one is plus di plus eji d tilde j. That should also be a nice object. But what are those? Top there, left. These are our derivatives. So our derivatives that came from string theory, they were clever enough. They are nice objects. The first one is minus di, and the other one is di bar, and therefore they transform nicely with the matrix M in the sense that di is mij dj, and d bar I is equal to m bar ij d bar j. And you can think of this as, since they are derivatives, as things that do this when acting on functions of x or functions of x prime. You have to use, if you wanted to just verify this again, even though it follows from this little theorem, which I left as an exercise. Use the chain rule, and you will get these equations. So our derivatives are also nice objects. Yes? Yes, prime should be on the right-hand side. Is that right? Just like here. I seem to be forgetting them. Yes, they are. The primes are there in page 14 of the notes. Okay, in many ways, everything is falling into place now with kind of tensors, but there's one object that hasn't quite fallen into a terribly nice position. Is this E, the E that transforms in the top blackboard with a linear fractional transformation. So you had objects in the fundamental that transform just with a little h. You have objects that transform with m and m bar. But capital E, as it is in the top blackboard, towards the right, middle, it's this linear fractional transformation. So what about E? That's sort of a little strange. But here comes the last thing that we need. So I'm going to try to move these blackboards correctly. No. This one will go up. This one will go up, and this down. Okay, I think we got it. Good. So let's erase a little. Microphone off. And I think this is dry enough. Yeah, it's dry. Okay, so E transforms in a complicated way. So E prime is somewhat complicated. It's AE plus B CE plus D. But there's something nice. Linear fractional transformation is something that you should always keep in mind. Linear fractional transformations are complicated, but their derivatives are always simple, much simpler. So if you have ever something like this, you should know that the derivative of E prime is related to the derivative of E in a much simpler way. And indeed, so you can say, for example, E prime plus delta of E prime should be H of E plus delta E. And that's how a little variation of E results in a little variation of E prime. And those are related in a simple way. Again, you have to do a little bit of ODD calculations. It takes in the notes, I did it explicitly. I think I didn't even ask you to prove anything there. And at the end of the day, in page 15, you get that delta E is actually M delta E prime M bar transpose. Look at that. E is an object that transforms with M and with M bar. So in terms of indices, you would write delta Eij is equal to MIP M bar JQ E delta E prime PQ. So this is telling you that E, in a sense, has the first index is unbarred because it transforms with M, and the second index is barred. You could put a bar if you want, because it transforms with M bar. So that's pretty nice. E is a complicated object. If you're going to write an action in terms of E, it's going to have linear fractional transformations. But if you're going to write it in terms of derivatives of E, it's going to transform nicely. So when we're going to try to write actions, we're going to use derivatives of E or variations of E. So this applies. Instead of delta, you could put a derivative with respect to x or x tilde. It would be the same thing. And even with our funny derivatives, our capital derivatives, di of E transforms with m di of E prime m bar transpose. You see, I didn't transform the d. So that's why I have a d here. I could put a d prime here and get another m. See, I didn't touch the d. It's like not touching the delta. Delta is here, delta is here. If I put a derivative, the same derivative appears here. And the m just is acting on the e itself. So if I don't change the derivative type, this equation holds. So on the other hand, if I want to write it in terms of completely primed objects, I have to use that di is another m acting on di prime. So at the end of the day, the summary of this is that if you write something like di ejk, this is a tensor that transforms with an m on this index, an m here, and an m bar there. It's a perfectly good tensor. If you write d bar I ejk, it transforms with an m bar on this index, an m, and an m bar here. It's a nice tensor again. If you have a g, it's somewhere there, top blackboard, it transforms with a m and an m here, or an m bar and an m bar. That, because it's doubled. If you had a g inverse, it would transform with an m inverse, or an m bar inverse and an m bar inverse. So here are our objects. We have d's, di's, di bars, g's, and derivatives of e's, and they're all nice tensors that transform with m's and m bars under ODD transformations. So that was supposed to be the end of lecture 1. I really believe it's no point to rush through things because otherwise nothing is really gained. So I wanted to give a clear picture of the ODD transformations because that's really the basis for understanding what you can write. So now we're going to turn really to writing actions and seeing how they work. So I'll take questions. Yes?
Is it not D also transform under ODD, right?
The capital D's? Yes, those boxed equations there with M.
I don't know how di is should I not put in the right hand side di prime and then?
You can. So you can, if I put the indices, this M index, let me put indices in this equation. di ejk would be MIP MJP di E prime, well, let me write it all, M bar KQ di E prime PQ. This is this equation with indices. You see, I didn't touch the di. You don't have to touch it if you don't want. But then at this stage, I can say, oh, di is it there that. So then you have mjp m bar kq m I L d L prime E prime PQ. And that's why I said at the end of the day, this is a tensor with all the indices transforming the way you would expect. Good question. Other questions?
So here you take E is not anymore constant.
Oh, good. That's correct. So I really went a little ahead of myself. E's were supposed to be constant, but as you're saying, we're going to try to write a field theory, so we will have things that are not quite constants in a few seconds. At this moment, you could say, oh, think of E as something that is not constant, but still transforms this way. If it transforms this way, this is true, and therefore if it's not constant, it works with derivatives. So the little confusion, it's a very good that you notice, is that E's at this moment, the way we've introduced, were supposed to be constant, so all these things are zero. But of course, now that we're going to try to write a field theory, we're going to try to add dependence on those variables, and they will not be constants. Yes?
The problem show us how we can get E from E prime, yes?
Yes.
But matrices M has some E, or it's E prime.
No, the matrix M has E by definition, yes.
But we obtain E from this formula, and this is like something like not the definition of E, but some equation from E, because we have E from the left-hand side and from the right-hand side. Because E, because M can see, because M has E.
That's right.
Yes, and so we have E from left-hand side and from right-hand side.
That's right. So it's a little unusual. These are not, the fact that these things depend on E is a little funny. So not everything on this right-hand side depends just on E prime. It also depends on E.
I multiply the inverse matrices and get that d prime I prime equals something that depends on the.
Right, you could do it. But in fact, these matrices are going to cancel all the time for us. So whether they depend on E prime is an issue of accountability. It will not matter. But it's unusual. Yes?
So the M also depends on this D and C, but the A and B part of the ODD
Yes, although they're not completely gone, because if you have an ODD matrix, A, B, C, and D are all related by the properties that they are made part of ODD. So some information about A and B is still there, but not all. Okay, so let's turn to lecture number 2. So I was getting this. This was. So what we're going to do now is try to write a double field theory. We're really ready to do that now. And so I will begin by writing an action. It's going to be a free action, though. But it's still surprising enough, the action. It's going to be written in all generality first. and then more explicitly in less generality. Okay, so here we go. Imagine your toroidal background. It's there. It has this capital EIJ constants, and now you want to let fluctuations begin to write a field theory. So you're going to have your EIJ, which were constants, and you're going to have a fluctuation around it, EIJ of x and x tilde. This is going to be imagined as a little fluctuation of this background. The symmetric part being the gravity fluctuation, the antisymmetric part, the Kalb-Ramond fluctuation. Then there's going to be a dilaton, d of x and x tilde. Now, since this is going to be a little fluctuation of this E, in ODD, when you postulate the ODD transformations, this is going to transform with an M on the first index and an M bar on the second index. Because it's a fluctuation, conceptually, it's a fluctuation of the capital E. So that's what it probably should be. No, you're trying to invent a theory, so you cannot be exactly sure what you're going to do, but you have some idea of what should be happening. So here it goes. Let's write a quadratic action. dx, dx tilde. We'll write that directly. It has to be doubled. So what are we going to have? Well, let's see. If we mimic gravity, we want to write things that make ODD sense. So, well, these indices are good ODD indices, EIJ. Well, there's boxes in gravity, and then we would have an EIJ here. This is one term I could write. What is box? Box, of course, is going to be our capital D, I, times di down. Or is it our bar I, bar down I? Well, it's either, because we have the constraint. Remember the constraint that d squared is equal to d bar squared.
So it cannot be di d bar I.
No, it cannot be that. It has to be, well, we could try something with di bar, and there will be some terms. We'll see. But at this moment, we think of a Laplacian that is an invariant, an ODD invariant, as this. Look, this is ODD invariant already. Let's look at it in more detail. This is Gij di dj. And remember, those transform with M and M, this with M inverse and M inverse, so this is invariant. And this is also invariant, happily, because G is very versatile. Remember, we said G can be thought as having barred indices or unbarred indices, so that makes this one also an ODD invariant, because these are barred indices, and G transforms with both. That's very crucial to the theory, that G transforms with both. So these are ODD good things. And what is EIJ up? EIJ up, we defined it down, so this must be GIP, GJQ, EPQ. You raise and lower indices with a background metric. Now, these indices, whenever there's contractions, the M's disappear, and now there's two indices up, so they transform with M inverse and M inverse. So M inverses and M inverses in here will go nicely as well, and it will form an ODD invariant thing. Now, remember, all the M's are functions of E, and m bars are functions of E, and therefore they don't interfere with the derivatives. You see, this transforms with two m's, this transforms with two m inverses because the indices are up, but the m's, even though they depend on E, they depend on the background E, so the derivatives don't care, and this is an ODD invariant term. So that's good, that's an ODD invariant term. Then there is this one, plus 1/4 d bar j eij squared. Well, what does it mean squared? It means that actually this is an object with an index down. So if you write something like ai squared, we really mean ai. And so you write this thing again and you raise the index I, and that's fine, that's a scalar, that's a good one. And then we can write plus 1/4 d I eij squared. And then dilaton couplings to the metric. Dilaton D coupled to the metric with I and J here. These indices are up, they've been raised. And here you can put an E, I, J, if this was a bar, because the I index with the I index form a scalar, the J bar index, this index, the second index on E is always barred. So this is also a good ODD tensor. And finally, you have -4, the usual kinetic operator for the dilaton. So that is a candidate action. Now, all these terms we could have written, and I think there's no other terms you could write, but the coefficients there were cleverly chosen so that this action is really meaningful and has a gauge symmetry. You see, this is supposed to be an action for gravity and dilaton fluctuations, so it must have gauge symmetry, and that requires all these coefficients to be quite nicely determined. So any questions about the action the way I've written it? What anything means there? Yes? Yes. Well, at this moment, you don't have it. It's a quadratic action. So even if you take the usual action, square root of minus g, by the time you write the quadratic action in Einstein's gravity, you also don't see that term. So we should see it eventually, but at this moment, we can't see it. Other questions? Well, we can use integration by parts, but all these terms don't quite, you can't eliminate one term and turn them into others by integration by parts. You can make them look a little differently, but that doesn't simplify it. So I claim there's no integration by parts here that will simplify this action. This is pretty much as simple as it gets.
Maybe if we consider E with one upper and one lower index.
No, I don't think you will simplify anything. You can try. Yes. A little louder. That's right.
So we can only get something like gravitational waves from such an action, but we cannot get something like black hole.
That's right. So this is a beginning. We're going to do more than this. But we should understand this one first. And as you will see, it has all kinds of peculiarities already. So it should have a gauge invariance. So let me write it down. delta Eij is d bar j of lambda I, and delta d is minus 1/4 of d dot lambda, which means d I lambda I. Here is a gauge invariance. Now, this gauge invariance is really instructive to check it, and I ask you to do it. You will have to use the constraint. So basically, some places you'll have a d squared, and you can trade it for d bar squared, and it should work out. It's a nice computation. And there's further gauge invariance. Look, the indices these are covariantly ODD nice. Why? D is going to be an ODD scalar. D is not going to transform under ODD. And therefore, here is a scalar. E has a unbar index. Well, that's the unbar of the lambda, but a barred index j, so that's why there's a d bar j here. But there's another gauge transformation, which is delta Eij. You could imagine it's a d on the first index and a new parameter, lambda bar j. You could bar the index or you may not, and for which the dilatot transforms with minus 1/4 d I bar lambda I bar. So that's another gauge invariance.
So the constraint d square equal d bar square is imposed in all these already.
The constraint that d squared equal d bar squared is additionally imposed, must impose. For E and for D and for the gauge parameters even, eventually. Everybody should be killed by the difference of d squared. So d squared is equal to d bar squared on all fields and gauge parameters. Ooh. Yes.
Those conditions were from the first quantization of the string.
Right.
Now, for the second quantization, we should also go.
Yes, so that's a good question. I said, look, first quantized spectrum satisfies this constraint. We're doing second quantized thing. Why should we impose the same constraint? Well, first quantization, the constraints on first quantizations are really things that give you the classical equations of motion. People that have looked into this thing called string field theory, they had the BRST operator. You study it in first quantization, but at the end of the day, for string fields, this is the equation of motion, that things are killed by the BRST operator. So the first quantized operators are really the tools we have to build classical field theories. So now you could say at this moment, you know, this constraint L0 minus L0 bar is something that since the beginning of string theory, people have been trying to go around it. Nobody has succeeded. I think it's pretty much impossible to go around it. Perhaps said in another way, the day anybody will go around this constraint, string theory is going to look very different. It will be a much more sophisticated theory than what we know, written in a much more sophisticated way. So actually, given this action, we played for a long time trying to get it to work without this constraint, and we never succeeded. That should not discourage you probably from trying, but I think it's, you know, there are many deep reasons why it's unlikely L0 minus L0 bar can be relaxed. So that's not something that's going to happen easily. Okay, so we have this action. I want to show you this action in plain English. This one should go down. This one should go up. This one should go down. Okay. So our purpose is to gain some intuition. So let's look at this action the way you should really look at it. Compare with what you know. So let's go back to fluctuations of G, the metric, and B. So how does it look? S2 that we wrote there. Now, I'm going to do a simplified case. So I'm going to assume the background B is equal to 0. So there's, remember, a capital E is G plus B. And unless you put B equal to 0, things are not so familiar. So let's put B equal to 0. G is still there. But here is what you get. So first line is going to be all kind of things that are familiar. And ij squared minus 2v I dj hij minus 4d d squared d. First line. These are partial derivatives hij. You may not recognize this formula, but actually that's the expansion of the scalar curvature plus the antisymmetric tensor field plus the dilaton to quadratic order. This is, if you take this famous action, square root of minus g e to the minus 2 phi r plus h squared with a number here, minus 112, I think, plus 4d phi squared, I think, minus 112h squared, the famous action. Expand G and B in H and B, and the phi is somewhat related to this dilaton. I said it last time, e to the minus 2 phi times square root of minus G is e to the minus 2d. I tell you, take this, expand to quadratic order, you'll get exactly this, which is nice. But that's not the end of this action. Now this whole line is repeated the same, identically, but with all the derivatives being d tildes. D tilde, and actually there's a change in sign here that it's sort of relevant, but minus 4d d tilde squared d. So only a change of sign and d tildes all over. That's something you would expect because of duality invariance. You know, some people might say these are the coordinates, some people say these are the coordinates. And then you get 1/4 bij d squared bij plus 1/2 dj bij squared. And this is coming from h squared. The conventional expansion of h squared, h, remember, is the derivative of b. So you didn't see any b here. And remember, eij is equal to hij plus bij. So here is the gravity and dilaton. Here is with dual coordinates. This is the antisymmetric tensor. And then again, plus the same thing with d tildes. And you would say, okay, that's good. Things with these, things with d tildes. And, but there's more terms, the really peculiar terms that have, these are all with two derivatives. So there are some things with two derivatives in which one is a d and one is a d tilde. So it will go like this. I'll write them here. There are three terms. dk hik d tilde j bij plus d tilde k hik dj bij minus 4d di d tilde j bij. Look how crazy. Minus 4d di d tilde j bij. This is a term that you would not see unless you keep both kinds of derivatives. So this theory is a double field theory. It includes winding and momenta. It is T-duality invariant. The one there, it's very nicely T-duality invariant. And here, of course, we've constrained to some particular background, but you still see the T-duality in which D and D tildes are exchanged for each other. And this is perfectly consistent and gauge invariant. It's really nice. So what symmetries does it have? Those were the symmetries there, but I don't think anybody can see those symmetries and say, oh, I understand. Let me write them again in plain English. So here they go. It's convenient to write this with parameters EI equal 1/2 of lambda I plus lambda I bar, and EI tilde, which is 1/2 of lambda I minus lambda I bar. So here are the gauge transformations. So I'm going to write them first like this in a way that you can follow them. dIEJ plus dJEI. This is the way gravity is supposed to transform under linearized diffeomorphisms. And with this transformation under linearized diffeomorphisms, it's a funny thing. Of course, you know, in a sense, you're familiar perhaps with the fact that gravity transforms with diffeomorphisms with Lie derivatives. We'll emphasize that. But there's an inhomogeneous part of the gauge transformations of gravity, and it's this term. Now, in the usual theory, when you write the conventional theory, this would be the symmetry, and then delta Bij would be 0. You say, oh, how come? B also transforms under diffeomorphisms. Isn't it a tensor? Yes, it is a tensor. It transforms under diffeomorphisms. It transforms linearly under diffeomorphisms. So there are terms here of order epsilon times fields that they don't appear at this order. And this is because essentially the flat metric breaks diffeomorphisms, that you sort of have this thing. So this is the usual transformation, should be like that. And delta D is equal to minus 1/2 del dot epsilon. Those are the familiar ones.
How can you add lambda and lambda bar if they are transformed by different matrices?
That's right. By the time I write this way, I'm hiding the ODD invariance. I'm making it totally unmanifest. That's okay. You can simply add them like that. We see we're sort of breaking a little bit of the ODD invariance because we're choosing some particular background. So the formulas, by the time you reduce to Einstein form or conventional Einstein form, you have broken ODD invariance because you don't have tilde derivatives anymore. So there's a little bit of breakdown that has to happen. Now, these are the conventional ones. And you might say, look, that still looks a little crazy to me because the dilaton, what's that thing? What is this thing? Well, actually, if you define a dilaton phi as D plus H over 4, where H is HII, then look at this. The gauge transformation of this phi would be delta D, and this, they would cancel, and that you will get delta phi equals 0. So that's how, to linearize order, the conventional dilaton is related to D and the trace of the metric. Okay, so this is not how this theory works. Here it's changed. So I'll put it in red. So this is conventional theory. This double field theory has here very funny things. Because you have the tilde derivatives, you get minus d tilde epsilon j minus d tilde I epsilon j minus d tilde j epsilon I. So actually, the diffeomorphism parameters that were not supposed to change the antisymmetric tensor, they do through the tilde derivatives. Their tilde dependence gives you the usual gauge transformation of an antisymmetric tensor, making everything quite symmetric and nice. The other transformations that you could call them delta tildes, EIJ, would be minus di epsilon j tilde minus dj epsilon I tilde. This is the usual Kalb-Ramond transformation of an antisymmetric tensor. And in the conventional theory, that would be all there is to it. But in this theory, the gauge parameters of Kalb-Ramond, which are E tilde, generate diffeomorphisms of the X tildes, because they have the same index structure. So actually, this generates a diffeomorphism using the tilde derivatives. And here, you get 1/2 d tilde E tilde. Now you can say, oh, okay, so for diffeomorphisms, I can produce a combination that is a scalar. How about for dual diffeomorphisms? I could try phi, and because of the sign, this time I have to put d minus h over 4, so that delta tilde of phi is 0. But this phi is not the same phi as this one. This should be phi tilde, because it's a different sign. So what's the conclusion? There's no, in double field theory, there's no scalar dilaton. You can make a scalar under diffeomorphisms, or a scalar under dual diffeomorphisms, but not a scalar under both. So in double field theory, or in string theory, D is a little better than phi. Phi is a good field by the time you're down to normal Earth. But once you keep living in the double space, which is the true space of string theory, there's no scalar. There's just D. D is nice, but there's no scalar anymore. Okay, this is the quadratic theory, and there is a cubic theory as well. I will say a few words about it and set up the stage of what we're going to do next. Let's see. This goes down. This goes down. 1 second. I'll listen to your question in a second. I think I wanted the other blackboard. No. this. I sort of have them, don't have them perfect, but that's okay, close enough. All right. Okay, this theory, as I mentioned, has ODD covariance, and there's a cubic theory. So you can keep constructing this with gauge invariance. So an S3, I will not write it in detail, dx tilde. And there's terms cubic in the gravity, Eij, and terms like di, ekl, d bar j, ekl, like this, and two more. And then there are dilaton E squared terms and dilaton squared E terms and dilaton cube terms. And everything can be written in about 5 lines. That is, in fact, quite economical with respect to usual expansion of Einstein theory. This, I say, is about 5 lines. If you expand the theory in usual variables, g and b and phi, it will be like 5 times longer. String theory is quite efficient in using this field E in a very clever way, and moreover, D is much better than phi, also for economic reasons. It really collapses the action quite a bit. So actually, we were able to construct this cubic theory in all detail, and the gauge transformations are changed, so delta lambda, delta of Eij, for example, which was d bar j lambda I, has more terms that can be determined, and the theory can be made gauge invariant to cubic order. And it's a double field theory, and it's totally general, and it's the kind of theory we would like to construct to all orders. But the construction has not been carried out beyond cubic order. It's difficult beyond cubic order, and it may or may not exist. Now, you might say a theory that exists so nicely to quadratic order, for which you can define a cubic interaction, it agrees with Einstein's theory in when x tilde is equal to 0, is T-duality invariant, it's everything quite nice. Why would it fail to quartic order to exist? Well, that's a good question, but remember, we're trying to build a theory that uses just a particular subset of string theory. So even though you can construct it to cubic order, it's not totally obvious that it can be constructed to all orders, keeping the gauge invariance. At any rate, that has not been achieved yet, and we can't quite, it gets messy enough that it becomes a difficult problem. So you want to solve it in a more clever way. Solving it in a more clever way involves putting more structure into this and understanding special cases. So what we're going to do next is attempt to understand this and to complete the construction of this theory under simpler circumstances. Not such a generalized double field theory, but a double field theory that is a little less powerful, but at the same time that we can construct till the very end. So that's what I will do. I want to explain this in some detail, but I will use last 5 minutes to explain what we're going to try to do. And once we put these extra assumptions or extra simplifications, we will get a double field theory that is not so powerful as the one we're constructing here, but it can be done to all orders, and it exhibits this Courant structure, this generalized metric structure, and all kind of nice things. So even though the double field theory that we will build will not be very as doubled as we would like it to be, it already will incorporate new elements into it, new geometrical structures, and it will be interesting enough. So that's what we're going to do in the remaining of these lectures. So what is it that we will impose? So far, suppose here, well, maybe that's a good way to say things. Here, in the nonlinear terms, you would have something like 1/2, for example, di lambda k ekj, plus terms like that. Now, remember that this field is supposed to satisfy the constraint. It's supposed to be killed by d tilde, must be 0. Now, this is fine if lambda is killed by d tilde equals 0. If it's killed by d tilde, then this is killed by d tilde. But now here you have two things. One term that is killed by d tilde and one term that is killed by d tilde. It's not obvious that the product is killed by d tilde because it's a second order operator. So in fact, if you have a field A that is killed by d tilde, and you have a field B that is killed by d tilde, the d tilde of AB need not be 0, because d tilde will act on the first, will act on the second, and then it will act in mixed ways. So the fact that one field is constrained and another field or gauge parameter is constrained doesn't mean that the product is constrained, which is what you need here. So that means that at this moment, if I want to proceed with the construction, if I have this thing over here, this product must be projected down to the subspace where the constraint holds, because this thing must satisfy the constraint. So if you have a product, of fields, then you need to project it down so that the constraint still holds on the product. So you would need to introduce projectors. But that, of course, is the reason why the construction becomes more non-trivial at higher orders. So what we're going to do is we're going to assume that the fields not only satisfy the constraint, but all products of fields satisfy the constraint. We'll assume that. So if all products of fields satisfy the constraint, actually, most of the difficulties disappear. But this is a very strong condition, so strong that we lose a lot of the doubling, in fact. So this condition, remember, this operator that I wrote here, which is 0, is also dm. So this is an ODD invariant constraint, but it's a constraint to require that this kills all fields and all products of fields is an ODD invariant constraint. So this is not incompatible with T-duality. So whatever you will construct will still have ODD invariance because it's an ODD invariant constraint. But nevertheless, it will be less general than what you want, because this is what string theory tells you. You should stop here and not put further constraints. But at this moment, it's hard for us to construct these to all orders unless we put more constraints. So we'll put more constraints, and we'll construct these things. But in doing so, I will have to impose this extra constraint, And this extra constraint says something that I want to write as a little theorem and basically explain that more. Little theorem. For a set of fields, A, B, C, such that dm kills all products. So I will write actually a set of fields A of x and x tilde, B of x and x tilde, such that dm kills all products. There is a duality frame x tilde x tilde I prime and xi prime. So you had x and x tildes. What I'm saying is that if those fields satisfy this strong constraint that it kills all products, not just that it kills all fields being killed is fine. That's what string theory tells you have to do anyway. But to kill all products is a lot stronger. If you have fields that depend on x and x tilde, such that all products are killed, in fact, there is a duality frame in which the fields do not depend on x tilde prime. They just depend on x prime. So basically, it says the following. You are working with doubled fields. They look doubled, and they are doubled. They depend on x and x tilde. But if you satisfy this constraint, there is some frame, some duality that you can find in which you would check that the fields are not really double, but depend on half of the coordinates. So once you're assuming that the fields satisfy this strong version of the constraint, it means that your action is doubled, but you could perform a duality and reach some set of x and x tildes in which the action just depends on x's, and it should reduce then to the conventional action. So by the time we ask this, the theory is doubled, but there is some frame where it is not. And therefore, since that frame need not be specified, you will still have the ODD invariance. The constraint is ODD invariant. So you will have a theory that physically there is a frame where it's not doubled, but it has the ODD symmetry and the gauge symmetry acting simultaneously. It's an ODD version, ODD invariant version of Einstein's theory. It's not as doubled as we would like it to be, but it still will have T-duality invariance, and it will be written as a doubled field theory because that's the way we can implement this symmetry. So that's really our task, and that task will be done to all orders. So it will be fairly geometrical, and the nice surprise is that in putting together the ODD covariance and the general covariance, the Courant bracket shows up and the generalized metric shows up. Those we will introduce next time, so we'll stop here. Thank you.